In today's world, words like green, renewable, and eco-friendly are all over the news. But when we talk about renewable polymers, what do we actually mean? Renewable means that a source is naturally refilled over a small duration of time. The definition of small duration actually changes depending on what you're talking about. Using fuel as an example, coal takes millions of years to form under very specific conditions, whereas trees take only tens of years to grow. Under this definition, trees would be considered a renewable resource. A polymer is a large molecule, sometimes known as a macromolecule. Polymers are made by linking long chains of short repeating units called monomers. In this first example, the monomer shown is propanol, and so the hypothetical polymer formed would be polypropanol. Polymers are used in almost every household item, and one of their most prevalent uses is in plastics. Most plastics are currently made from the byproducts of the petroleum industry and are produced from the distillation of crude oil. To create desired plastics, the oil is separated into different types of monomers, which undergo a polymerization process to link them together. One key example of this is polystyrene. Polystyrene is made in a multi-step process from ethylene and benzene, which naturally occur in coal and can be synthesized from petroleum from oil. Styrene monomers are formed by adding an aluminium chloride catalyst. The monomers are then polymerized by chain polymerization by adding an initiator, for example benzoyl peroxide. The initiator activates the monomer and allows them to start linking together. A chain can then be formed, which gradually grows until the desired chain length is reached. This forms polystyrene. A renewable alternative to polystyrene is polylactide, also known as PLA. The formation of polylactide starts with a glucose-rich raw material such as corn. It is then fermented to form lactic acid. Once the lactic acid has been extracted, it can be put under vacuum and heated to reflux. This forms short chains of polylactide, however they're not long enough to be useful. The short chains are then heated with a tin octoate catalyst. They are then put under high pressure with an initiator, and this allows them to form long chains of polylactide. Polylactide can be used as a replacement for polystyrene packaging, but it can also be used to make plastic cutlery and in 3D printing. Another very common polymer, which is used to make water bottles and other plastic packaging, is polyethylene terephthalate, or PET. The raw materials to make PET both come from petroleum or coal tar. The PET is made up of two monomers which alternate in the chain. This makes it an alternating copolymer. PET is formed from monoethylene glycol, or MEG, and tetraphthalic acid. MEG can be produced by oxidizing ethene gas from oil. The reaction between MEG and terephthalic acid is a condensation polymerization reaction. This is because it eliminates one molecule of water. Terephthalic acid can be produced by oxidizing P-xylene. This is extracted from crude oil or coal tar. Both of the monomers used in PET are extracted from crude oil or coal. There's a finite supply of both of these resources, and it will soon run out. So an alternative is to use monomers such as biomeg and FDCA. The polymer that is formed from these two monomers is called PET. Biomeg is a version of MEG produced from glucose. There are two ways to produce biomeg. The first is by fermentation and processing to form 2 molecules of biomeg and 2 molecules of carbon dioxide. This has a 67% yield. The second is to use new ray technology and hydrogenolysis to break apart the glucose molecule into 3 biomolecules with a 100% theoretical yield. The other monomer used is FDCA. This is furan dicarboxylic acid. The Dutch company Avantium have recently commercialised the production of PET from FDCA. It has a slightly different structure to tetraphthalic acid, and this gives PET some different properties to PET. One of these differing properties is permeability. PET has a lower permeability than PET. This means it can help to improve shelf life of food products when used in packaging. PET allows fewer oxygen molecules to penetrate into the packaging and fewer carbon dioxide molecules to leave, meaning products such as carbonated drinks will stay fizzy for longer. 2 other benefits of PET over PET are that PET has a better heat resistance and a higher tensile strength. The formation of PET is also especially environmentally friendly, as the process uses only hydrochloric acid, which can be extracted from table salt, and the hydrochloric acid can be fully recycled back into the process. It is also done at room temperature and atmospheric pressure, so no heating or pressurization. There are downsides to these renewable polymers though. PLA is biodegradable under commercial composting conditions. However, commercial is key here, as it doesn't refer to typical back garden conditions. Instead, it requires a controlled temperature and humidity with the correct microorganisms to truly biodegrade. We currently don't have the infrastructure to commercially compost the volume of PLA we would be producing, so it is likely that much would end up in the oceans, which would take more like 80 years to decompose. PET is not biodegradable, but it can be processed in existing recycling plants. There is another issue here, however, as only about 42% of household waste is actually recycled in the UK. It is important to remember that most issues around environmental concerns are a balancing act. The bigger picture is often hard to keep in mind when we find solutions to one area of the problem, and this can risk worsening another, more concerning area. Renewable polymers and biodegradable polymers are good solutions to our supply and disposal problems. However, they still contribute to our overall carbon footprint, and we should be doing all we can to reduce our need for these polymers too.